In this example, we're going to test an equation for symmetry, and really we're testing the graph of this equation, but without graphing it. So recall from your text that there are 3 different types of symmetry that a graph can have. So your symmetry could be with respect to the x-axis, with respect to the y-axis, or with respect to the origin. So if the graph is symmetric with respect to the x-axis, then we investigate changing the y value. If we're investigating symmetry with respect to the y-axis, we investigate changing the x-coordinate. And if we're looking at symmetry with respect to the origin, then we change both the x and the y. And here's what I mean by change. If we take an original point off from this graph that I know is on the graph of this function, and it's going to have coordinates x, y. And x and y would actually be numbers, but I'm going to keep it very generic right here. If this equation has symmetry with respect to the x-axis, then the point x negative y will also be on this graph. So if an original point was 2, 3, then 2, negative 3 would also be on this graph. Similarly, if this equation has symmetry with respect to the y-axis, and I take an original point that I already know is on the graph, then negative x, y should also be on the graph. And then with the origin, what we're looking at is swapping both coordinates to their negative counterparts and seeing if they're still on the graph of the equation. Now, it would be very time-consuming and tedious to actually verify every single point on the graph of this equation. So what we're going to do is check the entire equation all at once. So here's the strategy for this. I note the change in each symmetry. We go from y to negative y when we're looking at symmetry with respect to the x-axis. In symmetry with respect to the y-axis, we change from positive x to negative x. And in symmetry with respect to the origin, both change. So here's what we're going to look at. I'm going to test symmetry with respect to, I abbreviate WRT, with respect to, with periods between, the x-axis. And what I'm going to do is substitute negative y for y in the equation. And I'm looking for the same equation to emerge, okay? If I substitute in a negative y for positive y, and it really doesn't affect the equation in any way, then this graph has symmetry with respect to the x-axis. However, if I substitute in negative y for positive y and it completely changes my equation, then it does not have that symmetry. Okay, so I will replace y with negative y. And simplify, combine like terms, until I get either the same equation or something completely different. So right now, there's not really much I can do. Maybe I'll multiply both sides of this equation by negative 1 to try to get y equals on the left-hand side. Distribute that negative 1 in. So you can see when you compare this equation to the original, you can see that each term now has a different sign from the original, which means I did not get out the exact same equation as the original. So this graph does not have symmetry with respect to the x-axis. Because these are not the same, they do not have that type of symmetry that I was testing for. So this graph does not have symmetry with respect to the x-axis. So now I'm going to run a similar test. I'm going to test for symmetry with respect to the y-axis, which means I'm going to replace each x in the original equation with a negative x. What I'm looking for is when I make that replacement, do I get the same equation or something different? So let's test for symmetry with respect to the y-axis. Again, I'm going to substitute negative x for the original x in the equation. So I'm going to have y equals, don't forget your use of parentheses. Okay, so I get negative x squared minus 3 times negative x minus 4. That is a minus sign there. Okay, so I will simplify. A negative x squared becomes a positive x squared. Negative times a negative is a positive, and minus 4. And at this point, I've simplified as much as I can, so I'm going to compare this to the original equation. Okay, so both equations have y equals a positive x squared. They also both have a minus 4 on the end. However, this middle term is different. Over here it's positive, and over here it's negative. So again, this is not the same equation, so it does not have this type of symmetry. Okay, so even if one term is different, if one small detail differs between these two equations, they are not the same equation. Okay. So since I didn't get the same equation, they do not have this type of symmetry. So there's one last check to perform, and that's to check for symmetry with respect to the origin. So what I will do is make both changes at the same time. So I really want to emphasize that you're making both of these substitutions at the same time, capital and right here. We're going to make this replacement and this replacement at the same time. So in my original equation, I will replace y with negative y and x with negative x. And I will simplify and see if I get the same equation. So I have on the left-hand side negative y. Again, a negative x squared becomes a positive x squared. Negative times negative is positive. And then in order to compare these two better, I'm going to multiply both sides of the equation by -1 so that I will have y equals in both equations. So distribute on the left-hand side. Okay, so I have simplified this as best I can, so I'm going to compare this to the original equation. And do these two equations match? Unfortunately not, right? We have a y equals a negative x squared versus a positive, negative, negative, positive, negative. These two are not the same. which means this graph does not have symmetry with respect to the origin. So yes, it is possible for an equation to have none of the above symmetries. It's also possible for an equation to have all three types of symmetry, or just one, or just two, etc. But so that means that you just need to test each one every time on the equations. And the way that you know that the graph has that symmetry is if you make the substitution and you actually get the same equation back.